Hello there, Mr. Sutton here with the AB Calculus 610 homework solutions on rate in, rate out. On this problem, I have tide removing sand from a beach at a rate modeled by R of t right here, and then a pumping station is adding the sand back at a rate given by S of t. And they're telling us that we're starting with 2,500 cubic yards of sand, and this is all from hours 0 to 6. So for part A, we want to know how much sand the tide is going to remove from the beach over this 6-hour period, with units of measure. Okay, well, let me put these both on my calculator because I know I'm going to need them both for later. So on my calculator, I'm putting my R of t removal function in y1, and then S of t, the pumping function here, that's going to be in y2. Now coming back here, how do I figure out how much sand gets removed from the beach? Well, I have to take my rate of removal right here and integrate that over the period from 0 to 6 hours, because that'll tell me the total amount of sand removed. So I'm going to write integral from 0 to 6 of R of t dt. And for that, I do need to go on my calculator. So let me quit out of here. And my removal, that was y1 that I stored that one in. So I'm going to do math 9 integral from 0 to 6 of alpha trace y1 dx. And let's just press enter. That's going to be 31.816. And what's the units going to be on this? Oh, the total amount of sand, it's the volume of sand. And let's see here, they said that we were using cubic yards per hour for the rates, so then cubic yards, or yards cubed, is going to be our units for the amount of sand removed. For this next problem, they want us to write an expression for y of t, the total number of cubic yards of sand in the beach at time t. So if you want to find the amount of sand that's actually on the beach, we definitely need these rates of change and some integrals of these to figure out the total amount removed and the total amount added, but we also can't forget this initial 2,500 that we're starting with. So I'm going to write y of t equals 2,500 plus, now we're going to talk about the sand that we added. That's going to be the integral from 0 to t of my s of t function, but I can't have the same variable inside, so I'm going to write s of x dx, and then 0 to t integral. And I can't, of course, forget about the sand that's being removed during this time period. So I'm going to subtract the integral from 0 to t of r of x dx. This is one way of writing it. Alternatively, you could actually merge these into one big integral and write 2,500 plus integral from 0 to t of s of x minus r of x dx. Either of these would be fine. For this problem, this part of the problem, they want the rate at which the total amount of sand on the beach is changing at time 4. So here was the overall amount of sand at any given time. So I just need to take y prime now to figure out the rate at which the sand is changing. So that gets rid of this 2,500, and then just plugging in t using our fundamental theorem, we just end up with y prime equals s of t minus r of t. Another way to think about it is if you want to know the total, the rate of at which the total amount of sand is changing, it's just going to be rate in minus rate out. So in order to actually figure out this quantity at time 4, I'm going to go back to my calculator, and I've created a third function in my y equals now, y2 minus y1. This is s of t minus r of t on my calculator. And I didn't really need to do this just for this problem, but I have a feeling I might need it on the next one, so who knows. It doesn't really cost me too much time to put that in there. And now I'm just going to do alpha trace and pull up y3, and I'm just going to plug in the value 4. So open parentheses, plug 4 in there, and enter. We get negative 1.909. What are the units on this? Well, this is the rate at which the amount of sand is changing with respect to time. So this is going to be the same units as R and S, cubic yards per hour. So negative 1.909 yards cubed per hour. For the last part of this problem, they want to know what time from 0 to 6 is the amount of sand at a minimum, and what is the minimum value. All right, so we're going to find some critical values here. I'm going to set y prime equal to 0 and solve that on my graphing calculator. Now recall that on the last part, the last problem, I actually defined y prime in my calculator as y2 minus y1, again s of t minus r of t, and I'm so glad I did that because now I have something in there that I can graph. I'm going to deselect r of t and s of t because I don't really want to see their graphs. I'm just going to graph this. And I'm going to do a window from 0 to 6 on my window here. because those are the only values I care about for this beach. And then zoom 0, zoom fit. And let's see what my y prime function looks like. So I'm going to be looking for places where this crosses the x-axis, the critical values of y prime. And it looks like it hasn't crossed yet. Oh, but no, wait, there we go. We've got one crossing right there. So I'm going to go ahead and do second trace now, 0. And let me just figure out where that is. Now let's see, where's my spider? There it is. So a little bit to the left, press enter. Move a little bit to the right, press enter again. And that's a value of about 5.1179 if we take it to 4 decimals. I'm going to quit out of my graph, and I'm actually going to store that value I just got as alpha A or alpha whatever letter you want, because I have a feeling I'm going to need to pull this value back again, and I don't feel like writing the whole thing or scrolling up for it. So now what I'm writing down for my work here, so I have this graph that I did. I don't actually draw the graph, but looking at the graph, I say that y prime of t equals 0 at time approximately 5.1179. And notice that I said t equals a here. So now instead of writing out this number, I can just write a whenever I mean this. Okay, so we have some options on this one. One option when you're trying to show a min is you could use the candidates test, which in this case means I have to plug 0 and 6, the endpoints, and also this critical value into my y function that I created a few problem steps back. Another option, if you didn't want to do that, is you could very quickly say y prime is negative on the interval from 0 to a, and y prime is positive on the interval from a to 6. Therefore, we have a local min at time a, and that would work. That would at least get you the time. But to find out what the minimum value actually is, you're going to have to plug this thing into y anyway. So that's why I'm going to use the candidates test on this one instead of that other method. All right, so let's start with y of 0. Well, y of 0 we don't need to do any fancy math for. The beach started with 2,500 cubic yards of sand, so y of 0 is 2,500. Great. Now let's do y of a. That's going to be the initial 2,500 I started with, plus the integral from 0 to a of y prime of t dt. And again, I'm really glad now that I stored my y prime as one of my y equals on my calculator, along with this a value. Let me go ahead and do that now. So here's what I've got on my calculator, 2,500 plus integral from 0 to a, where I stored this value, alpha trace y3, again, that's where I stored y prime, and then dx. And all of that comes out to approximately 2,492.369. Okay, I'm not done yet though because I've got to do the other endpoint, 6. Now we're decreasing after we get to a, so there's really no way this 6 is going to be any smaller than what we just got here. But again, if you're doing the candidates test, you have to show all the candidates. So 6 gets an honorary mention. We got 2,500 plus integral from 0 to 6 of y prime. And this really doesn't take me too much longer to do on the calculator because I'm just going to arrow up and grab this input from before. And instead of going from 0 to a, I'm going to go from 0 to 6 and press enter. So just one little small change there. And now I've got this other value, which is still pretty close, 2,493.277. But now looking at all these, I see that my minimum is happening at time A, and that's 8 hours. And it's actually going to be 2,492.369 cubic yards of sand. For this problem, on a certain workday, the rate in tons per hour at which unprocessed gravel comes to a gravel plant is modeled by this g of t function. So this is the rate at which gravel is coming in. And this happens between times 0 and 8. Now, at the beginning of the workday, our plant has 500 tons of gravel, and during the hours of operation, we're processing the gravel at a constant rate of 100 tons per hour. So we have a rate in, given by this g of t. We have an initial value of 500. We have a rate out of 100, just a constant rate out. For part A, they want g prime of 5, and interpret your answer with correct units in the context of the problem. So I'm going to start by putting my g function in my calculator. This is a calculator problem. So here we are. I'm in my y1. I just entered this whole function in here. And now to do g prime of 5, I'm going to quit out of this. And I'm going to take the derivative of what I just entered at time 5. So I'm going to do math 8 and then dx, and I'll do alpha trace y1. So I'm taking the derivative of my g function that I just put in there, and that's happening now at x equals time 5. This gives me a value of negative 24.588. And that's great for that first point, but now I have to actually explain what I just figured out. So g itself was the rate at which gravel was coming in. G prime then is the rate of the rate at which gravel is coming in. So if I have a negative rate, then that means at 5 hours, we have to put the time in there, at 5 hours, the rate at which unprocessed gravel is arriving, since this is negative, that means this rate itself is going down, is decreasing by 24.588. And what's the units going to be on this? Well, the original rate was, let's see, amount of gravel per hour, tons per hour. So this is going to be tons per hour squared. The rate at which the tons per hour is changing is in tons per hour squared. For part B, they want the total amount of unprocessed gravel that arrives at the plant during our hours of operation on the workday. So the rate at which gravel arriving, again, is given by this g of t function. If I want to find the total amount that has arrived, I need to integrate the rate of arrival over the whole workday. So that's going to be from 0 to 8. So the first thing I'm going to write here is the integral from 0 to 8 of g of t dt. And then I just have to do that on my calculator. So here on my calculator, I already have g of t entered as y1. So I'm just going to do math 9, 0 to 8 for this integral, and then alpha trace y1, dx, and let the calculator do its thing. So that ends up being about 825.551. And this is gravel arriving, so this is tons. For part C, they want to know if the amount of unprocessed gravel in the plant is increasing or decreasing at time 5 and justify that. All right, so there's two processes that are going on. This G function is giving us gravel to work with, so this is happening throughout the day. But we also have this 100 tons per hour rate at which gravel is being processed. So if you want to know if the amount of gravel is increasing or decreasing, we have to compare whether the rates at time 5, which one's bigger. So let's first find what g of 5 is, because that'll tell us how fast we're processing gravel at time 5. So looking to find g5, and we're going to go to the calculator for this. On my calculator, I again stored g as y1. So y1, open a parentheses and plug 5 in, gives us about 98 and change, 98.141. And that's tons per hour again. So now, how fast are things being processed at time 5? Well, the good news is that's a constant processing rate of 100 tons per hour. This rate of gravel coming in is less than the rate that gravel is being processed at. So less is coming in than is being processed. That means the overall amount of unprocessed gravel is going to be decreasing at this time because we're processing it faster than it's coming in. For this last part of our problem, we want to know the maximum amount of unprocessed gravel during our hours of operation. So I basically have to find critical values for a function that describes the rate at which the gravel is changing. The problem is I don't have a function like that defined yet. So I'm going to define a new function, u of t. This is the amount of unprocessed gravel. And then I can define u prime of t as the rate in, g of t, minus the rate out, minus 100. So this now tells me the rate at which gravel is changing overall. Okay, so let me find some critical values for u prime of t. Let me graph this on my calculator. To help me out with this, I've defined a very simple function, y2, as y1 minus 100. This again is just g of t minus 100. I am going to deselect my g of t function that I have in here. So I just want to graph that second one. And for my hours of operation, my window, I'm going to go from 0 to 8. And then let me zoom fit that one, zoom 0. So here's my rate at which gravel is changing. And there's only one critical value right here at whatever this is. Let me find what that is. Second trace, zeros, appears to happen between 4 and 5. And I'll press enter one more time. So that's about 4.9235. I'm actually going to quit out of here and store that as a value. I'm going to store that as A, so I can use it later. And now let me just write here that my t value is A equals this stuff that I just saw in my calculator. So now I can say A instead of writing all this on paper too. Good for me. All right, I'm going to use the candidates test now to see what gives me the highest value. This critical value, the starting value of 0, or the ending value of 8. So at 0, I know I already have 500 tons of gravel. They gave us that. To figure out U of A, though, I need to do that 500 plus the integral from 0 to A of U prime of t. And for that, I need the calculator. So on my calculator, I've got 500 plus the integral from 0 to A of y2, because that's where I stored U prime. This comes out to about 635.376, and that's tons of gravel. And now let me do the same thing at the other endpoint of 8. That's going to be 500 plus integral from 0 to 8 of all this. That's a little easier on the calculator because I can just go to my input from before and replace this A with 8. And now press enter to get 525.551. So out of all of these then, our maximum amount of gravel happened at time A. It was 635.376 tons of unprocessed gravel. For this problem, which involves a whole lot of reading and a graph, we have some water in a storage tank modeled by a continuous function on the time interval 0 to 7. And let's see here, we've got the rate at which the water enters the tank, this f of t function, 100 t squared sine of radical t. And yes, this is a calculator problem, so you should probably enter this in your calculator at your earliest convenience. Now we also have a rate out. Here's the rate at which water is leaving the tank. It's this cute little piecewise function. From 0 to 3, it's 250. From 3 to 7, it's 2,000. They've actually graphed both of these functions for us down on this graph here, and they even told us where they intersected. I mean, it was a calculator question, so you could have found this on your own, but this was nice of them to provide this information. So here's one intersection and the other intersection, which they gave us. They also told us we're starting with 5,000 gallons. All right, now that we've got that set up, part A, they just want to know how many gallons of water enter the tank during the interval 0 to 7, round to the nearest gallon. Well, for this, we need to do our entering rate, which is this f of t function here. So we're going to need the integral of this f of t function, dt, from 0 to 7. And this will give us the amount of water in. So let's do that on the calculator. So to start things off, I'm actually going to put this in my y1 because I'm sure I'm going to need it later. Let me quit out of there now, and let me do math 9 to take my integral from 0 to 7 of alpha trace y1. That's where I stored my f of t function, dx. And this comes out to how much? 8,264 if we round to the nearest gallon. So that's in gallons. For part B, we want to know on the interval 0 to 7, the time intervals during which the amount of water in the tank is decreasing, and give a reason for each answer. Okay, so we have a rate of increase and a rate of decrease. Rate in, rate out. Our water is going to be decreasing, our water level's decreasing when the rate out is higher than the rate in. Now, to see where this happens, we can actually look down at the graph. So keep in mind, this piecewise function is water leaving. The continuous smooth function here is the water coming in. And we see that the rate out, g, has a greater value than f on a few of these intervals. So from 0 to whatever this intersection is, they said it was 1.617. This is one interval on which g of t is greater than f of t. And after that interval, it looks like f of t is higher until you get to this little jump in the piecewise function. At that point, and this happens at 3, from 3 until this other intersection, 5.076, from 3 to that number, g is again higher than f. So from 0 to 1.167, and from 3 to 5.076, and then after that, f overtakes g, and it's that way for the rest of the graph. So these are the intervals where g is higher, which means that these are the intervals on which the amount of water is decreasing. For this problem, we want to find the time when the amount of water is the greatest and compute that greatest amount. So we're going to start by defining W of t to be the water amount, so I can now talk about the water amount. And I don't know exactly what this function looks like just yet, but I know the derivative of this, the change in the overall water amount, is going to be the rate in, f of t, minus the rate out, g of t. So that's what w prime looks like. And we're going to have to keep in mind when we use this that g of t has two different rules depending on which interval we're in. All right, so we need to get some critical values now for w prime, and we'll test those critical values along with the endpoints of 0 and 7 in wt, again, whatever wt looks like. So let me start by differentiating between two types of critical values. We have critical values where w prime is 0, and we have critical values where w prime is undefined. So the critical values where this is 0, those are going to be places where f and g have the same value. So for example, these two intersections here, the 1.617 and the 5.076. But there's also a critical value on here where this derivative is undefined. So this spot right here at t equals 3, g of t does not actually exist there. So trying to involve g of t in w prime makes w prime undefined at t of 3. So that's another critical value that we might have to test. Now the good news is not all these critical values are possibilities for being maximums on our function. Two of them, in fact, are local mins. So if you look at this first one here, where f starts out lower than g and then becomes greater, well, if f starts out lower and then becomes bigger than g, that means we're changing from negative to positive w prime right here. So this is actually a local min, and we don't even have to consider it. Up here, the same thing happens. We're changing from negative to positive w prime, so that's also a local min. The only place where we change from positive to negative w prime, where we start out with f being higher than g and then end with f being lower than g, is this undefined derivative value at t equals 3. So that I only have to consider this value, I'm going to write w prime changes from positive to negative at t equals 3 only. That establishes I'm only looking at local maxes in terms of critical values. All right, so now that I've eliminated the need to test out these 2 points as critical values, let me go ahead and test out the 3 that I have, the 3 here and the 0 and the 7. So w of 0 is the amount of water at time 0. They gave us that. It's 5,000 gallons. To figure out w of 3, I need to take that initial 5,000, and I have to add the integral of w prime from 0 to 3. But now w prime is going to have a specific shape when we go from 0 to 3. F of t is still f of t, but g of t is actually 250 from 0 to 3. So I'm going to write integral from 0 to 3 of f of t minus 250 dt. And now I'm going to do this on the calculator. So here's what this looks like on the calculator. My 5,000 is over here if we scroll to the left. I've got integral 0 to 3. y1, that's where I stored my f of t function, minus a 250. And we end up with 5,126.591. We'll have to round it off eventually, but I'll wait until I see that this is actually the max before I round it off. All right, continuing on, we want w of 7. So if I want to do w of 7, probably the fastest way to do it is to take the value at w of 3 and just add the integral from 3 to 7 of w prime. So I'm going to start with w of 3, which I'll just plug in this number here. And then I'm going to add integral from 3 to 7 of f of t minus, now the g of t function is actually 2,000 from 3 to 7. So I'm going to do f of t minus 2,000 in there. And now going back to the calculator to do this, for my w of 3, I'm just going to arrow up and pull this value that I just got for w of 3. Now I'm going to add the integral, so math 9, from 3 to 7 of, and now we have alpha trace y1 minus 2,000. And let me get over here for my differential, x, press enter, and that comes out to 4,513.807. All I have to do now is pick the highest value. Out of all of these, that's this 5,100, and if we round it to the nearest gallon, 27. So that many gallons, that's our max, and that happens at time 3 hours. For this problem, we have a tank at time 0 containing 48 gallons of water, and from 0 to 4 minutes, the rate of water flowing in the tank is given by this E of t function.
while water is leaking out at a rate described by L of t. We just want to know how many gallons of water in the tank at time 4. So this is basically a rate in, rate out, FTC type of problem. We can say that our water in the tank at time 4 is going to be this initial amount of 48 plus the integral from 0 to 4 of rate in minus rate out. So E of t minus L of t dt. And I'll plug all this in my calculator now. So to make this a little bit easier to work with, I've entered E of t as y1 and L of t as y2. And now let me take my integral. So I've got 48 plus math 9, so the integral from 0 to 4 of, now I'm going to do alpha trace y1 because that's E of t, minus alpha trace y2 because that's L of t, and I'll put a dx on the end, giving me a total of 82.749, and that's going to be answer choice B.